Welcome back. Regression and inference. As usual, we're interested in this sample of students really only to the extent that they tell us about the population of students from which we assume they were a random sample. When we were considering correlation and inference, we had to assume our data set was a random sample from a bivariate normal population, a very demanding assumption really. For regression, we don't need such a demanding assumption. For x, we only need to assume interval scaling. For y, we need to assume interval scaling and that it is normally distributed at each value of x. So at each value of x, we have potentially a very large number of observations of y, and we need to assume that they come from a normal distribution and that we have homogeneity of variance of y across all values of x. So all those different populations of potential y values have a standard deviation or a variance that's the same at each value of x. Also, if we want to make predictions about individual cases, we have to assume that the case we're considering comes from the same population that the data came from, and in particular that the x value we consider is within the range of x of our data set. In practice, it usually makes very little sense to make predictions for x values that lie outside the range of x in our data set. In regression, usually our main focus is on the regression equation because this tells us about the relationship between y and x, particularly from the point of view of predicting y from x. So here's the equation we've calculated for this data set, and we're usually especially interested in the slope. Here, 0.7795, say round about 0.8. What does that 0.8 tell us? It tells us that on average, for a single point increase in pre-test, we'd expect on average to get an increase of about 0.8 of a point in post-test score. So that's really a very strong relationship. 1 point here, on average 0.8 of a point there, and that's the slope of this line. But we have only a small data set, so the confidence interval on this slope is really quite long. If we think about what is the slope in the underlying population for predicting post-test from pre-test, then our point estimate of that slope is around 0.8, but the confidence interval runs from about 0.5 up to just over 1. So that's a long confidence interval, corresponding to regression lines with a considerably smaller slope, about 0.5, or a somewhat greater slope of about 1.1. Let's consider another of our data sets, say the data set for well-being against body satisfaction for the whole group of 106 males and females. There's the regression line, and the slope here is about 0.82, meaning that for 1 point increase in body satisfaction, on average we'd expect about a 0.8 increase in well-being, and that's the slope of this line. And the confidence interval on that slope is from about 0.5 up to about 1.1. So still a moderately long confidence interval, despite the fact we have a somewhat larger sample size of 106. Now I'm back with a small Thomason 1 data set. There's the regression line, and I'm going to mark some individual values. So for x is 8, I'm predicting y hat is about 10.5 from this line. Now think of what we have at x equals 8. We have a whole population of potential y values. That's assumed to be normally distributed. What is our best estimate of the mean of that distribution of potential y values? Answer, 10.458. What's the 95% confidence interval for our estimation of the mean of that population of potential y values? For that, we need to click here at red 11, and we see this red interval here, which is from about 9.1 up to about 11.8. And that's our 95% confidence interval for the mean of all y values at x equals 8. And if I change x to a different value, well then I get this 95% confidence interval for the mean of all y values at this particular x value. And you can see what's happening here. If I move this up to, say, an x value of around 16, I get this confidence interval for the mean of the population of all y values at this x value. Does it make sense that these confidence intervals are a bit shorter in the middle? Well, you can think of the sort of uncertainty we have in this line estimated from our data. If we could sample over and over again, lots of samples of size 12 from the same population, this line would bounce around. And it would bounce around up and down a bit, but it would also bounce around by rotation, corresponding to different slopes for our estimated regression line. And so the combination of a little bit of up and down and a little bit of rotation means that there's greater uncertainty out at the ends than there is in the middle. So it makes sense that the confidence interval for the mean of all y values at a particular x value will be longer towards the extremes of the range of x values we are dealing with. So there we are back at x equals 8. We have one more interval to consider, and that's a prediction interval. And there it is, this green interval here. And here we're answering a slightly different question. We're saying, well, at x equals 8, for somebody who gets an LSAT pretest of 8, what sort of range of possibilities are there for their post-test? So here we're considering making a prediction for an individual student who happens to score 8 on the pretest. And the answer is there's a 95% chance, there's a 95% prediction interval that this individual student's post-test will lie between about 7.1 and 13.8. Why such a long interval? Because we're talking about an individual student, not the mean of all students here. That's what this confidence interval in red refers to, but the prediction interval for an individual student, and that's much longer. So we have a confidence interval on the slope, we have a confidence interval for the mean of y at a particular selected x value, and then we have a prediction interval for individual cases at a particular x value. Which should you choose? Well, it depends on what you want. If you're interested in the overall predictive relationship between y and x, well, then you'll probably want to know about the amount of uncertainty in our estimate of slope. If you're interested in predictions at a particular value of x, then this confidence interval tells you about the uncertainty in estimating the mean of all y values at that particular x. But if you're interested in having some idea of the amount of uncertainty in predicting the score that an individual student who scores 8 on the pretest will have, then this prediction interval may be what you want. But certainly regression is a wonderfully valuable technique and allows us not just to understand in a slightly different way the relation between variables, but to make inferences from a data set to the underlying predictive relationship between variables in what we assume is the underlying population. And that can be extremely valuable.